all the security stuff I have to do. So a couple of things before we get started today. Now, first things first. You got your homework set. When's it due? Thursday. And you got to do all this good stuff online. Here's the big issue. So you can actually come over here and click on this thing. And actually you can actually see the homework set, which is really what I wanted you guys to do. And I labeled it here, but somehow I forgot to change the little fall to spring thing up here and forgot to change it to a spring. But a couple of problems. Number one, question number 13 here and question number 13 on, let me get over here to the Canvas side here. So over here, and let me go over what you guys are supposed to do. Go over here to modules. Hurry up and wait for a second. There's some little typo issues and stuff like that. We're still working on trying to get this thing working for us and stuff. So I'm going to scroll all the way down here to where you're supposed to put in all your answers and stuff like that. So here it is. There's your homework number 3, test review number 3. All right, and what I'm going to click on here is the preview thing here because I don't actually submit mine. And so you hear all your questions. And I'm going to go all the way down to question number 12. All right, a couple of things. Here is our question number 12. This one is, what a surprise, find the equation of a tangent line type thing here. Okay? Let's go to the next problem. Question number 13. Now read the question now. What does it say? F of x is equal to 3e to the 1 minus x squared times natural log of x. You got to do the product rule, plug in the number, get the slope of the tangent line, and then point slope formula, all that good stuff. Let's go to the next problem. What does it say? Calculate the derivative of this and find the equation of tangent line. See, that's actually not the question. That's the same question as the one before it. But the answers are all different now. So if you come over here to the actual test review and go to number 13, there's the actual question. Does that make sense? I cut, copied, pasted, and I forgot to go back and change number 12 and type in all the stuff. And now that you guys have already started taking the quiz, I can't go in there and edit this crap. So here's the question number 13 here. You actually have to print out the form to see the question. The answers are there. I mean, I got the answers all typed up, but the question doesn't match up. This is problem number 13. The other problem that I see now that I didn't realize at the time was over here. You see problem number 21? What did I do? I put A, B, C, D. You with me? Let's go over here back on this thing. Problem number 21. Let's scroll down here to problem number 21. Problem number 21 is this guy right here. Which one of these guys is the derivative? I made it a multiple choice question. All right. The next problem, if you click on it, oops, wrong button there. Click on it. It says it's question number 22. It's not 22. It's B. You see. But I didn't realize that the computer's going to renumber these things. So I had A, B, C. It went 22. So C is going to be 23. D is going to be 24. So you see problem number 22 right here? It's actually number 25. The questions are right. It's the computer I'm trying to get to match up to the system. So again, you guys are doing the learning curve here. But this the sheet is correct. So if I come over here to back to the computer and look at question number 25, you'll see question number 25 actually matches up to question number 23 in terms of the homework set. Use logarithmic differentiation. There it is. Use logarithmic differentiation. I'm learning about how the system is working, so welcome to my world of new systems and trying to input all this good stuff. And like I said, problem number 13, the question is wrong, but the answers are right. Go to question number 13 on the sheet. The sheet is key right there. Go to that one. You'll actually see the question, and you'll see which one it's supposed to match up to. Does that make sense? Again, trying to give you guys some helpful hints and stuff like that on this thing. Now, also on this particular homework set, because I wanted you guys to do it just like a regular homework set, I only allowed you guys to have one attempt on this thing. But being that I there's still some learning curves for me on this one, do you guys want to have more than one attempt on this one just in case? Are you going to pay me like money or something or other? All right, fine. I'm going to give you 2 attempts. Because I want this like a homework set, all right? Because of the things not merging up, I'm going to give you guys 2 attempts. So does that make sense? But that's it. After 2, we're going to take your lowest grade. All right, so let's see how I do this. Okay, I'm going to go this. I'm going to go edit. You're just going to see exactly how I do this stuff after I get this stuff coded. And let's see here. We're shuffling the answers. Time limit, no time limit. Allow multiple attempts. Here it comes. To keep the highest score. Allow attempts. 2 attempts. Okay? All right. And we will save. Now, so you've got 2 attempts. You can go, if you've already done it once and you got upset that you couldn't go in there because of these little issues, I am going to allow you guys to have 1 more attempt. So you got 2 attempts on this thing, okay? All right, but remember, the key to it is this particular, make sure you print it out and do the problems there because that's the actual questions. There you go. All right. So, let's pick up where we left off. So today's lecture is going to be on finishing up section 3.7, which you do have some questions on the homework set and will be on your test. But 3.7 is the end, but no time like the present. I'm going to move on into section 4.1. Might as well learn some more stuff from the next chapter. But chapter 4 is going to be on your 4th test. Chapter 3.7 is the end of this test material. Okay? So, let's remind ourselves of what we've done thus far. What we have done thus far has been, chapter 3.7 is on L'Hopital's rule. But when do I get to use that famous L'Hopital's rule? There's only 2 cases I use L'Hopital's rule on. What is it? It's got to be either 0 over 0 or, plus or minus, infinity over infinity. You with me? That's the only 2 cases I can do L'Hopital's rule. So, we have other indeterminate forms here. The other indeterminate forms are 0 times infinity. Is it 0? Is it infinity? Well, sometimes, yes. Is it 5? Well, sometimes. Okay, indeterminate. You can't tell what's going on. Another one, infinity minus infinity. Do they cancel? Well, sometimes. Sometimes the answer is 0. Sometimes this infinity is bigger than this infinity by, 5. So the answer is 5. Sometimes this infinity is bigger, so the answer is negative infinity. So, it's indeterminate. You can't tell what's going on. And then there are the exponential cases. 0 raised to the 0 power. Anything to 0 power is supposed to be 1, but what if you start out at 0 raised to the 0 power? Is that 0? Is it 1? Well, yeah, sometimes. And it could be 5. Who knows? Infinity to the 0 power. Well, anything to the 0 power is supposed to be 1, but wait a minute. If the base is infinity, well, maybe the answer is infinity. Well, sometimes it is. And the famous 1 to the infinity. I know you're thinking 1 to the infinity should be 1. Not necessarily. It depends on how fast you go to 1 versus how fast that exponent blows up to infinity at you. So you don't always get 1 on something. It's indeterminate. Okay? These are exponential indeterminate because you got something in the exponent. So I'm grouping this stuff together in 3 cases. The 0 times infinity case, the infinity minus infinity case, and the exponential. 0 to infinity, infinity to 0, and 1 to the infinity. I'll group that as one big case. So there's 3 more cases of indeterminate forms. Okay? Now, the first one is the famous 0 times infinity. So traditionally with 0 times infinity, you start out with a product here. The trick. You want to call it a trick? Fine. I'll use that word. The trick, when you got 0 times infinity, is to put one of your functions in the denominator. Why? Because L'Hopital's rule only works with fractions. 0 over 0 and infinity over infinity. It's got to be a fraction. So when you got a product, what you're going to do is either stick the first function on the bottom or the second function on the bottom. But you got to do it algebraically. So to stick f of x on the bottom, you're going to be 1 over f of x, because when you divide by a fraction, you invert multiply. So this is still the same thing as this. You're just trying to change the form. Or maybe it'll be easier for you to stick g of x, the other dude, on the bottom. Fine. You put g of x on the bottom, it becomes 1 over g of x in the denominator, because when you divide by a fraction, you invert multiply. So these guys are exactly the same thing. But this will put it in L'Hopital rule format, so you can take the derivative of the top over the derivative of the bottom and then redo your limit stuff to get your answer. But remember what I said before, very important. When you're doing L'Hopital's rule, you got some kind of eventually fraction where you got 0 over 0 or infinity over infinity. You're going to take the derivative of the numerator over the derivative of the denominator, clean it up first, and then redo your limit. Does that make sense? You've got to clean it up first. There's a lot of algebra to be done with this stuff. So, the goal of 0 times infinity is to make fractions out of it. Well, sometimes the fractions are easy to do and sometimes they're not. So let's take a look at this problem here. I'm going to take the limit as x approaches 0, and I'm going to do this on the plus side just to show you what's going on here of this particular problem. Of the cotangent of 2x, put little parentheses around my angles there, times the sine of 6x. So this is the limit as x approaches 0 on the plus side of the cotangent of 2x times the sine of 6x. Here's my problem here. Here's the deal. If you plug in 0 right now, the cotangent of 0 on the plus side is actually positive infinity. The sine of 0, whether it be on the plus side or the minus side, is 0. It's the famous infinity times 0. But as I mentioned to you before, the trick on doing infinity times 0 or 0 times infinity is to make fractions out of it. Now, you're right, I could stick one of these guys in the denominator, I can stick cotangent in the denominator, I can stick sine in the denominator, but better yet, everything in trig is based upon what two trig functions? Sines and cosines. Instead of trying to stick somebody on the bottom, when it comes to trig, why don't you rewrite it? What is the definition of cotangent of an angle? Tangent of an angle is sine over cosine. What's cotangent? Cosine over sine, but it will turn it into a fraction. So this is equal to the limit as x approaches 0, and let's say it's on the plus side, of cotangent is the cosine, in this case cotangent of 2x would be the cosine of 2x over the sine of 2x times the sine of 6x. Yeah. But also remember this. To do L'Hopital's rule, you've got to have a numerator function and a denominator function. You want that fraction thing going on. So again, I'm going to clean this up. This would give me the limit as x approaches 0 on the plus side of the cosine of 2x times the sine of 6x divided by the sine of 2x. But before you try to do any kind of weird L'Hopital rule, check it, make sure it's the right format first. Here we go. Plug in 0. The 2 times 0 is 0. Cosine of 0 is 1. 6 times 0 is 0, but the sine of 0 is 0, and 0 times 1 is 0 over the sine of 2 times 0, which is 0. Sine of 0 is 0. Yep, it's 0 over 0. By doing the algebra on the function, you've turned it into a L'Hopital rule, 0 over 0. So now I'm going to apply L'Hopital's rule. But what is L'Hopital's rule? What you do is, when you got this fraction, you take the derivative of the numerator and divide it by the derivative of the denominator. What is the derivative of the cosine of 2x times the sine of 6x? And what rule would you use? Product rule. Derivative of the first times the second plus the first times derivative of the second. What's the derivative of cosine of 2x? For that, I got to use the chain rule. What's the derivative of cosine? Negative sine. The inside, the 2x stays the same, times derivative of the inside, which is 2. That's derivative of the first times the second, times the sine of 6x, plus the first, the cosine of 2x, times derivative of the second. What's the derivative of the sine of 6x? Again, chain rule. Derivative of sine is cosine. The inside 6x stays the same, but 10 times derivative of the inside, which is 6. There is the product rule for the numerator. Then divided by the derivative of the denominator. What's the derivative of sine of 2x? Well, chain rule again. Derivative of sine is cosine. The inside angle, 2x stays the same, times derivative of the inside, which is 2. Now, plug in your number. When I plug in x is going to 0, this will be negative the sine of 0 times 2 times the sine of 0 plus the cosine. 2 times 0 is 0. Times the cosine of 6 times 0, which is 0, times 6, all over the cosine of 2 times 0, cosine of 0, times 2. With me so far? Now, tell me what these trig functions are. What's the sine of 0? 0. What's the cosine of 0? 1. So we end up getting pretty much negative 0 plus 1 times 1 times 6 is 6 over 2. Negative 0 is 0 plus 6 is 6 divided by 2. What is my answer? 3. The solution is 3. Does that make sense? Did I lose you guys anywhere? So here is an example of the original problem being 0 times infinity. And what do I get? 3. Indeterminate form. I can rig it to make it anything you guys want me to make it. Does that make sense? You got to just work out the problems. Questions? All right. Here's no. First rule limit. Plug it in. I want you to take the limit as x approaches 0 on the plus side of x to the 4th times the natural log of x. First rule, plug it in. See what you got. This will be 0 on the plus side to the 4th power times the natural log of 0 on the plus side. Because you can't take the log of a negative number, you can't actually plug in 0. 0, your official limits have to go from both sides here. So we're on the plus side here. 0 raised to the 4th power, that's still 0. But what is the natural log of 0 on the plus side? No, it does exist. It's positive because it's on the plus side. Remember your log graph goes to the point 1, 0, flows out this way, but as you get close to 0, it goes straight down. So as I approach 0 on the plus side, it's going towards negative infinity. It's 0 times negative infinity. Now, whether it be plus or minus infinity, we don't care. It's a 0 times infinity style problem. And then here's the trick. Understanding when you got this situation, what to do. When you've got a 0 times infinity, the trick is to turn it into a L'Hopital rule problem, you've got to put one of these terms in the denominator. I've got two terms. I've got x to the 4th, and I've got natural log of x. Which is the easiest term to stick in the denominator? X to the 4th. Why? Because to move something that has an exponent to the denominator, all you got to do is change the exponent to be negative, right? So this is an algebra thing. So this problem actually is the same thing as the limit as x approaches 0 on the plus side of the natural log of x divided by x to the negative 4th. Because the negative exponent in the denominator, you bring it to the top and make them positive, so it's the exact same equation. But remember what this guy really is. He is actually 1 over x to the 4th power. That's what x to the negative 4th is. And just to also remind you, what is 1 over 0 on the plus side? What does that equal to? 1 over 0 on the plus side. You remember? This is from calculus, from chapter 1 actually. Chapter 1.6. What is 1 over 0 on the plus side? That's positive infinity. What is 1 over 0 from the minus side? Negative infinity. What's 1 over infinity? Whether it be plus or minus, doesn't matter. 0. These are some of your limit laws that you were supposed to have memorized from way back when in chapter 1 here. So, the natural log of 0 on the plus side is negative infinity. 1 over 0 on the plus side to the 4th power is still going to be 1 over 0 on the plus side, and 1 over 0 on the plus side is positive infinity. So when you plug it in, you actually get negative infinity over positive infinity. You don't care about the plus or minus. It's infinity over infinity, which means what do I get to do? L'Hopital's rule. This will be equal to the limit as x approaches 0 on the plus side of the derivative of the numerator divided by the derivative of the denominator. What's the derivative of natural log of x? 1 over x, things we have memorized. What is the derivative of x to the negative 4th? Bring it down front. Negative 4x to the subtract 1. Negative 5. Does that make sense? L'Hopital rule. Derivative of the top over derivative of the denominator. Bottom. Okay? Now, clean it up. Before you chunk in 0, clean it up. This is the limit as x approaches 0 on the plus side of 1 over x divided by what's negative 4x to the negative 5? That's the same thing as negative 4 over x to the 5th. And to clean it up, you've got a fraction divided by a fraction, so you invert and multiply. So this is the limit as x approaches 0 on the plus side of 1 over x times x to the 5th divided by negative 4. What cleans up? Well, this x on the bottom cancels with one of those x to the fifth, makes it x to the fourth. So this is equal to the limit as x approaches 0 on the plus side of x to the fourth over negative 4. You cleaned him up first. And now plug in the number. We're taking the limit as x approaches 0 on the plus side. So this is 0 on the plus side raised to the fourth divided by negative 4. 0 on the plus side raised to the fourth is pretty much 0, officially on the plus side, divided by negative 4. What's 0 divided by negative 4? 0 on top makes it 0. So the limit as x approaches 0 on the plus side of x to the fourth times natural log of x, which turns into that 0 times infinity. Well, here's an example where you actually do get 0 on that problem. So the goal here, and this is what I'm doing the rest of chapter 3.7, is to take these indeterminate forms of 0 times infinity, infinity minus infinity, and 0 to the 0, 1 to the infinity, infinity to the 0 power stuff, those indeterminate forms, and to convert it into a L'Hopital rule. Here's another one. First rule of limits. Plug it in. Well, take the limit as x approaches infinity of x to the fifth times e to the negative x to the fourth. This would be infinity to the fifth power times e to the negative infinity to the fourth power. Infinity to the fifth power. Infinity times infinity times infinity times infinity times infinity. One big old infinity. Times e to the infinity to the fourth power is still infinity, but it's negative that. Power first and then do your sign. But wait a minute. Some more stuff you need to know, just to remind you. What's e to the negative infinity equal to? 0. E to the infinity is infinity. E to the negative infinity is 0. Okay? So, because that negative exponent put him on the bottom, and e to the infinity is infinity, but when the infinity is on the bottom, it goes to 0. This turns into infinity times 0. Another one of these non-L'Hopital rule indeterminate form types. Does that make sense? So, what's the trick? When you have infinity times 0, you got to turn it into a fraction so you can do L'Hopital's rule. I've got a question for you. You've got x to the fifth times e to the negative x to the fourth. The trick is, anytime you got 0 times infinity, is to put one of these terms in the denominator. And you want to put the easiest term in the denominator. The one that's easiest to put in the denominator. Which one is that? Is it x to the fifth, or is it the negative e to the negative x to the fourth? Well, let's see here. You're right. I could put that x to the fifth in the bottom just like we did up here and just make him x to the negative fifth. But wait, he's not the easiest dude. Look at the other guy. It's e to the negative x to the fourth. He already has a negative exponent. So what happens when I stick the guy with the negative exponent in the denominator? It's just going to become a positive exponent, and that's much easier to manipulate. Does that make sense? So the e, in this example, the e to the negative x to the fourth is the easiest guy to stick in the denominator. And so you would end up getting x to the fifth divided by e to the positive x to the fourth. Does that make sense? Because he's already a negative exponent, so when you move him to the denominator, he's going to turn positive. So now, plug it in, just to show you. Infinity to the fifth power is infinity. Infinity to the fourth power is infinity. And e to the infinity is infinity. It is infinity over infinity, but that is L'Hopital's rule. So I apply L'Hopital's rule to this guy, and I end up getting the limit as x approaches infinity of, what's the root of the numerator? What's the root of x to the fifth? 5x to the fourth. Divided by what's the root of e to the x to the fourth? Chain rule. What's the root of e to the x to the fourth? What's the root of e to a function? Got to know these rules. The root of e to a function is e to the function, chain rule, times root of the exponent. So the root of e to the x to the fourth would be e x to the fourth times the root of the exponent. What's the root of x to the fourth? Or x to the third. Clean him up. The x cubed cancels with x to the fourth, leaving me an x on the top. So this is the limit as x approaches infinity of 5x divided by ex to the fourth times 4. I put the 4 out front here. Plug in infinity. What do I get? Well, 5 times infinity is infinity over infinity to the fourth is infinity. E to the infinity is infinity. Still times 4 is still infinity. I got infinity over infinity again. So guess what I'm going to do? I'm going to do her again. L'Hopital rule. Again, this will be equal to the limit as x approaches infinity of, drew the top. What's derivative of 5x with respect to x? 5. 4 is a constant, leave it alone. What's derivative of e to the x to the fourth? Well, derivative of e to a function is e to the function times derivative of the exponent, which is another 4x cubed. This cleans up to become the limit as x approaches infinity of 5 over 16 x cubed ex to the fourth. However, plug in infinity now. You get 5 over 16 times infinity cubed e to the infinity to the fourth power. Infinity to the fourth power is infinity. E to the infinity is infinity. Infinity cubed is infinity. So you've got 16 times infinity times infinity. Infinity times infinity is not indeterminate. It's big infinity, right? Times 16 more is infinity. So you pretty much get 5 over a really big infinity. But when the infinity is in the denominator, what does it go to? 0. 1 over something really large is small. It goes to 0. Answer 0 to this problem. Does that make sense? Questions? So, in these last 3 examples, how do I handle 0 times infinity, plus or minus infinity? You're going to take one of the 2 guys, typically the easiest guy, and put him in the denominator to make fractions, and it will turn into a L'Hopital rule problem. Okay? What about the next type? Examples of the form infinity minus infinity. Here's the deal. Infinity minus infinity. The trick, if you want to call it a trick, I'll call it a trick, is to do algebra on this thing. You're either going to factor or get a common denominator. That is the pattern of the infinity minus infinity indeterminate form. And again, by factoring it or getting it into a common denominator, the ultimate goal is to turn it into a L'Hopital rule kind of a problem. So let's take a look at this guy. And I'm going to do the same thing as what I did on the first one. I want you to take the limit as x approaches 0, and I want to make it easy for myself. So I'm going to approach 0 on the plus side, okay, so I can actually describe what's exactly going on here. Of the cosecant of ax minus the cotangent of ax. Now, here's the deal. What's the definition of cosecant? 1 over sine of ax. When I plug in 0, the sine of 0 is 0, and on the plus side, it is on the plus side. And 1 over 0 on the plus side is infinity minus cotangent is cosine over sine. So the cotangent of ax is the cosine of ax over the sine of ax. Same deal. When I plug in 0, the cosine of 0 is 1 over sine of 0 is 0. On the plus side makes it plus side. So 1 over 0 on the plus side is infinity. It's actually an infinity minus infinity problem when you take the limit as x approaches 0 on the plus side. That's why I did it that way. Does that make sense? But here's the deal. When it comes to trig and doing these kind of problems, first thing I'm going to do is convert it to my happy world. I'm not a big fan of the cosecants or the cotangents and all that other good stuff. I like typically 3 trig functions, sine, cosine, and worst case scenario, I'll do a tangent for you. That's pretty much it. So when I run across a cosecant of ax, what's the definition of cosecant? So I'm going to do algebra on this thing. So this is equal to the limit as x approaches 0 on the plus side of 1 over the sine of ax. The cosecant of ax is 1 over the sine of ax minus the cotangent of ax is what? cosine of ax over the sine of ax. And you'll notice now that I actually do have a common denominator, right? Which is the sine of ax. So this is equal to the limit as x approaches 0 on the plus side of 1 minus the cosine of ax divided by the sine of ax. All I did was do algebra on the trig, but in doing this algebra on the trig, with this infinity minus infinity, I actually have a common denominator. Put it one big common denominator, which means I got a fraction. Now let's check it now. Take the limit as x approaches 0 on the plus side of 1 minus the cosine of ax divided by the sine of ax. A times 0 is 0. Cosine of 0 is 1. And 1 minus 1 is 0. The sine, a times 0 is 0, and the sine of 0 is 0. And all this algebra turned it into a 0 divided by 0 L'Hopital rule type. So now I'm going to apply my famous L apostrophe H L'Hopital rule. So this will be equal to the limit as x approaches 0 on the plus side of the derivative. What's the derivative of 1 with respect to x? 0 minus, what's the derivative of cosine of ax, and what rule would I use? Chain rule. Derivative of cosine is negative sine. The inside ax stays the same, but then you got to do times the derivative of the inside. What's the derivative of a being a constant times x? A. Derivative of 5x is 5. Derivative of ax is a. Divided by what's the derivative of the sine of ax? Well, chain rule again. Derivative of sine is the cosine of ax. Then chain rule times derivative of the inside, which is a. So I'm going to clean this up. This is equal to the limit as x approaches 0 on the plus side of a negative. Negative makes it a positive. Sine of ax times a divided by the cosine of ax times a. But I'm not done cleaning it up. What cancels on this thing? A's pretty much canceled itself out. And I'm left with the limit as x approaches 0 on the plus side of the sine of ax over the cosine of ax. So when I plug in 0, this will be the sine of a times 0 on the plus side divided by the cosine of a times 0 on the plus side. Now I did that for your benefit. A times 0, regardless of what a is, it's 0. The sine of 0 is, what's the sine of 0? I'll try again. Sine of 0. 0. Divided by a times 0 is 0. And the cosine of 0 is 1. And I got 0 divided by 1. And when the 0 is on top, what do I get? Answer 0. So here's another example of infinity minus infinity, which ends up canceling out and you actually get 0. Does that make sense? Questions? Okay. So the trick is either to factor or to try to get a common denominator. This one was a common denominator. If I got something that's in common, then I'm going to factor it out. So here's another one. Take a look at these guys here. I've got 0 to the 0, infinity to the 0, and 1 to the infinity. These are the exponential indeterminate form type. And there's going to be a trick to these guys, and I'm going to give you guys steps to do this one. Do you guys remember when we did some problems, especially taking the derivative of problems, where I have variables in the base and variables in the exponent? There was only one way in the world to take a derivative of something that has a variable in the base and a variable in the exponent at the same time. You remember what that was called? Logarithmic differentiation. Okay, you got to do the log of both sides, right? Logarithmic differentiation. It hasn't changed in these problems because with these three forms, you're typically going to have a variable in the base and a variable in the exponent at the same time. Let me show you. Look at this first example. What is the limit as x approaches 0 on the plus side of x raised to the x? First rule of limits is plug it in. I'm going to get 0, I'm finding it on the plus side, granted, to the 0 on the plus side. And here's the old question. What is 0 to the 0? Well, anything 0 power is 1. But when you start out with 0, you got nothing. Does it change? Is it still going to be nothing? Is it 0? Is it 1? Well, it depends. Let's find out what this one is. This 0 to the 0, let's see. All right, first thing you get is this. Because you got a variable in the base and a variable in the exponent, in these three cases, that's what you get. So the first thing you want to do is you want to call the function y. So let y equal x raised to the x. Okay? The second thing you want to do is you got to bring down that exponent. There's only one thing in the universe that brings down exponents. What's that? Logs. I'm not going to choose any log. I'm going to use the natural log. So step 2, you want steps? I'll give you steps. Step 1, set the function equal to y. Makes it easier for you stuff. Step 2, take the natural log of both sides. So the natural log of y equals natural log of x to the x. Step 3, clean up using those wonderful log properties. So I get the natural log of y equals, what's the natural log of x raised to the x? Where do exponents get to go when you got a log in front of it? Out front. That's cleaned it up. X times the natural log of x. And then, step 4, you got the natural log of y is equal, put your limit back in there. Limit as x approaches 0 on the plus side of x times the natural log of x. And now we'll go calculate this thing. Well, I've changed the format of the problem thanks to taking the log. If I plug in 0, what do I get? I get 0 on the plus side times the natural log of 0 on the plus side. That's 0 on the plus side times, what's the natural log of 0 on the plus side? Negative infinity. So what in essence I have done is change this 0 to the 0 power stuff into a 0 times infinity. See previous example. When you have 0 times infinity, what was the trick? Anytime you got 0 times infinity, the trick is always, to get it into a L'Hopital rule format, is put one of these guys in the denominator, make a fraction out of it, right? Which is the easiest term to stick in the denominator? The x or the natural log of x? Which one is easier to put in the denominator? The x or the natural log of x? The natural log of x, put in the bottom of the denominator, I got to put natural log of x quantity raised to negative 1. Well, that's a pain. The easiest thing to stick in the denominator, because it's x to the first power, is the x. So this will turn natural log of y is equal to the limit as x approaches 0 on the plus side of the natural log of x divided by x, but stick them in the denominator, you've got to change the power to a negative. So it's x to the first, officially x, but when you put him in the denominator, he's now x to the negative 1. Clean it up, you get the same thing back again. X to the negative 1 in the denominator, negative exponents in the denominator go to the numerator and become positive. So it's x to the first makes it x. So these two guys are the same thing. And if you plug in 0 on this guy from the plus side, the natural log of 0 on the plus side is actually negative infinity. X to the negative 1, to remind you, is the same thing as 1 over x. When you plug in 0 on the plus side, what is 1 over 0 on the plus side? Positive infinity. Using our limit laws from chapter 1. And it's infinity. Who cares about the signs? It's infinity over infinity. Which means now I get to apply L'Hopital's rule. So applying L'Hopital's rule to this guy, you get the limit as x approaches 0 on the plus side of, here we go, derivative of the numerator divided by derivative of the denominator. No chain, no quotient rule, anything like that. It's just derivative of the top over derivative of the bottom. What's derivative of natural log of x? 1 over x. What's derivative of x to the negative 1? Negative 1, x to the negative 2. Does that make sense? What did I say about after you do L'Hopital's rule? Clean it up. So this is equal to the limit as x approaches 0 on the plus side of 1 over x divided by negative 1 over x squared. What do I do when I have a fraction divided by a fraction? Invert and multiply. So this gives me the natural log of y is equal to the limit as x approaches 0 on the plus side of 1 over x times invert and multiply x squared divided by negative 1. I want you to see I literally, there now you can see it, I literally flipped the denominator fraction. Clean it up. What's x squared divided by x? X. So this is equal to the limit as x approaches 0 on the plus side of x goes into x squared x times divided by negative 1. Now, plug in your number. What's the limit as x approaches 0 of x divided by negative 1? 0 over negative 1, which makes the answer what? 0. But that ain't my answer. Remember, y was the original function. Y was this x to the x. We had to take the natural log of both sides. So therefore, the natural log of y is equal to 0. What gets rid of a natural log so you can go back and solve for that y, which was the original problem? What gets rid of natural logs? E, raising e to both sides. E raised to the natural log of y is equal to e raised to the 0. This cancels, which implies y, which was that original problem, limit as x approaches 0 on the plus side of x to the x is actually equal to, what's e to the 0 power, also known as? E 2.718. A number to the 0 power is 1. The answer to this problem is 1. You do the natural log, both sides, get that limit, and then you got to do e to that answer. So, here's the deal. Whether I have 0 to the infinity, infinity to the 0, or 1 to the infinity, I'm going to do the same trick every time. I'm going to, once I had identified it as one of these type of indeterminate forms, I'm going to set it equal to y, the original function, take the natural log of both sides, clean it up, and then do the limit answer of that guy, and then the last thing I'm going to do is get rid of the natural log to go back to the original function. So you're going to see a lot of these answers of e to a power. This one is e to the 0, which is 1. Take a look at this guy here. Again, you got one on web work, you got one on your homework set, just like it, that's due on Thursday. Here it is. Take the limit as x approaches infinity of 1 plus 2 over x raised to the 3x. First rule of limits, plug it in. This will be 1 plus 2 over infinity raised to the 3 times infinity. What's 2 divided by infinity? When you've got a fraction and infinity is in the denominator, what's this thing going to go to? 0. Plus 1 is 1. 3 times infinity is infinity. So here is an example of the exponential indeterminate form type of 1 to the infinity. What is 1 raised to the infinity? Is it 1? Is it infinity? Is it e to the 6th? Is it e to the negative 6? What is it? Well, let's find out. When you got one of these exponential indeterminate rule types, what's the next thing you're going to do? Go back, take your function, which is 1 plus 2 over x raised to the 3x, and set it equal to y. That's your step number 1. I'm repeating the steps. This is what I did with a few seconds ago. Step 1, call it y. Step 2, what do we do? Take the natural log of both sides. Natural log of y equals the natural log of 1 plus 2 divided by x raised to the 3x. Step number 3, you cleaned it up. So you get the natural log of y is equal to, what's the natural log of 1 plus 2 divided by x raised to the 3x? Where do exponents get to go? Out front. So this is 3x times the natural log of 1 plus 2 over x. Now, let's redo the problem. You got the natural log of y equals the limit as x approaches infinity of 3x times the natural log of 1 plus 2 over x. Plug it in. Let's see what you get. You're going to get 3 times infinity times the natural log of 1 plus 2 divided by infinity. What's 3 times infinity? Infinity. What's 2 divided by infinity? Infinity on the bottom. What does it go to? 0 plus 1 times the natural log of 1. But wait a minute, that's something we know. What's the natural log of 1 equal to? 0. Any log base, whatever, of 1 is always 0. All this work was just to figure out, once we took the natural log, we turned it into an infinity times 0. With infinity times 0, what are you going to do? You're going to put one of your variable terms in the denominator to make fractions, right? Which term are you going to move? the x, or the natural log of 1 plus 2 over x. Which is the easiest thing to move to the denominator? The natural log guy or the other guy? All right. So, here we go. We're working on step number 4 here. So you get the natural log of y equals the limit, I'll draw a little line so we don't get confused on this thing, is the limit as x approaches infinity of 3x times the natural log of 1 plus 2 over x. Right here is where people will screw this up. So what term are you guys going to move to the denominator? Which one are you going to move to the denominator? And you just screwed it up. The x. 3 is a constant. Never move a constant. He doesn't need to go anywhere. Constants stay where they're at. And that, I'm picking on you because that is such a common mistake for most Calc 1 students. They know there's, with 0 times infinity, they're supposed to put one of the terms in the denominator. They're going to move that constant right along with him. Constants never move. Leave constants alone. That 3 stays right where he's at on top. I'm just going to move the x, never touch a constant. So it'll be 3 times the natural log of 1 plus 2 over x divided by x to the negative 1. I'm going to put that x to the denominator and make him have a negative exponent. Now, I'm going to clean them up just for your sake. So this is the limit as x approaches infinity of 3 times the natural log of 1 plus 2x to the negative 1 divided by x to the negative 1. Because I'm going to remember, I'm going to take derivative of the top over derivative of the bottom, and no one likes to take derivative of 2 over x. That's the same thing as 2x to the negative 1. So here we go. Right now, if I happen to plug in infinity, just want to show you what it is. What's 2 divided by infinity? Infinity in the denominator makes it 0. Plus 1 is 1. The natural log of 1, things we know from high school, is 0. So it's 0 on top over x to the negative 1, same thing as 1 over x. 1 over infinity is 0. 0 infinity in the denominator makes it 0. So it's a 0 over 0, which means what? L'Hopital rule it. So this gives me the natural log of y equals the limit as x approaches infinity. 3 is a constant. Here we go. Times, here we go. What's the derivative of the natural log of 1 plus 2x to the negative 1? What's the derivative of the natural log of a function? It is, that's why you got to know those derivative rules real well, 1 over the function, 1 plus officially 2 over x, times, chain rule, the derivative of the inside. What's the derivative of 1 plus 2x to negative 1? Derivative of 1 is what? 0 plus, what's the derivative of 2x to negative 1? Negative 2x to the what? Negative 2. Divided by, that's the derivative of the top, 1 over, 3 is a constant, leave it alone. Derivative of natural log of a function is 1 over the function times the derivative of the inside. What's the derivative of x to the negative 1? Negative 1x to the negative 2. L'Hopital rule. I took derivative of the numerator over derivative of the denominator. You do enough of these problems, you can start looking at the answers and see what they are. Now, what did I say about after you do L'Hopital's rule? Very important. Before you plug in the infinity or the 0 or whatever number you're going towards, you got to do what first? Clean them up. The trick on all this is algebra. What cleans up on this thing? What do you see canceling? X to the negative 2's cancel. This cancels with that. Strict multiplication divisions when things cancel. What are you left with? This implies that the natural log of y is equal to the limit as x approaches infinity of 3 times negative 2 is negative 6 divided by negative 1 is 6 over 1 plus 2 over x. I just cleaned them up and I put my constants. 3 times negative 2 divided by negative 1 makes the 6. Now, plug in infinity. When I plug in infinity, I get the natural log of y is equal to 6 divided by 1 plus 2 over infinity. What is 2 divided by infinity? 0. Infinity on the bottom goes to 0. Plus 1 is 1. I get 6 over 1 which is equal to 6, because remember this is being added there. You get 6. But wait a minute. That's not y. That's not the original problem. It's the natural log of y equals 6. And then the last trick with this type of stuff, so here comes your step number 5 type thing here. What gets rid of that natural log? She can solve for the original problem, which was y. E to both sides. That cancels. So you get y, which was equal to the original problem, the limit as x approaches infinity of 1 plus 2 over x raised to the 3x actually equals to e to the 6th power. Does that make sense? So, to answer the $64 question, what is 1 to the infinity? Clearly, it's e to the 6th. In this example, I can make it into any kind of answer you want it to be. Does that make sense? The very important problem, and there's a lot of work to be done for this particular problem. Any of these exponential types, you've got to do this type of thing too. You've got to set it equal to the function, you got to take natural log of both sides, and then you got to do your limit stuff. And typically you're going to turn it into, a number time, infinity times zeros, put it on the denominator. Yeah?
Does that only work for 1 to the infinity, or does it work for any other? Does it work for other numbers?
No, all those examples. 0 to the 0, infinity to the 0, or 1 to the infinity. It works for all of those. These 3 of these 5 steps to be able to get the answer.
So when you have like a 5 to the infinity, is that not?
5 to the infinity? That'll be infinity.
Okay.
It's the idea of 1, well, no, I can rig that to be something different too. It's a number, basically, to the infinity power. But traditionally, no, that's not true. That's not true. Let me rephrase that. To answer your question, if I have any other number in the base than 1, 5 to the infinity. See, you're going to 5, you're not going to 1. See, 1 to any power is supposed to be 1, but it's the infinity and then the argument between the two. 5 raised to a power, you're going to power up a 5, that's going to get bigger and bigger and bigger and bigger automatically. So the answer is going to be infinity. It's got to be a 1 to the infinity, because 1 times 1 times 1 doesn't blow up on you. It doesn't go to 0 either. It stays at 1. So it depends on how fast you go to 1 versus how fast the exponent goes to infinity to see if it's going to blow up or blow down. You can get 0, you can get 1, you can get infinity, you can get e to the 6th. You can get lots of different answers. Okay. Well, here's another one. Same type. Take the limit as x approaches 0, and I'm going to, again, do this. When I'm going after 0, traditionally I pick a side. I'm a big fan of the 0 on the plus side. You'll see why in a second, so I can show you what's going on here. So take the limit as x approaches 0, officially on the plus side, of 1 minus 7x raised to the 1 over x. First rule of limits, plug it in. I'm going to get 1 minus 7 times 0, officially on the plus side, raised to the 1 over 0 on the plus side. What's 7 times 0? 0. What's 1 minus 0? 1. But what is 1 over 0 on the plus side? It's one of our limit laws. What's 1 over 0 on the plus side? Positive infinity. So this is an example of 1 to the infinity. So what are my steps? Drill, drill, drill. Step 1. Set the function equal to y. Y equals 1 minus 7x raised to the 1 over x. Step 1. Step 2. You got variables in the base. Variable is the exponent. Can't handle that. So what are you going to have to do to be able to handle that? Natural log both sides. Natural log of y equals the natural log of 1 minus 7x raised to the 1 over x. Step number 3, and I just remind you, I'll write that words in there. Clean up. Using log properties. Where do exponents get to go when you got logs out front? So you end up getting the natural log of y equals 1 over x times the natural log of 1 minus 7x. So rewrite that, the natural log of y equals, go back and put your limit back in there. Limit as x approaches 0 on the plus side of 1 over x times the natural log of 1 minus 7x. The way I have it written right now, here we go, plug it in. When I plug it in, this is for your benefit, I'm going to get 1 over 0 on the plus side times the natural log of 1 minus 7 times 0 on the plus side. 7 times 0 is 0. 1 minus 0 is 1. The natural log of 1 is 0. 1 over 0 on the plus side is positive infinity. So now we went from 1 to the infinity by doing the log on both sides. I turned it into the traditional infinity times 0. With infinity times 0 or 0 times infinity, you've got to put one of these terms in the denominator. Which one's the easiest thing to put in the denominator? Well, you want to put the 1 over x in the denominator or the natural log of 1 minus 7x in the denominator? What's the easiest thing to put in the denominator? And it's even better than that. And what happens when you put 1 over x in the denominator? What's it going to turn into? X. Don't try to put 1 over x. No, don't do that mess. Just clean it up. You're multiplied by 1 over x. Can't you just make this one big old fraction here? What's 1 times natural log is natural log. So just clean up the algebra here. This is the limit as x approaches 0 on the plus side of the natural log of 1 minus 7x. When you multiply by 1 over x, that pretty much put the x in the denominator, and it's so much easier to clean up. 1 over x is crap divided by x is what 1 times 1 over x is. Does that make sense? Now, plug in your 0 on the plus side. When I do that, I'm going to get the natural log of 1 minus 7 times 0 on the plus side divided by 0 on the plus side. This is the natural log of 7 times 0 on the plus side is 0. 1 minus 0 is 1 times 0 on the plus side. Natural log of 1 is 0, pretty much over 0. It's already set up for you for L'Hopital's rule. 0 divided by 0. So the natural log, so L apostrophe H, my code I'm going to do not L'Hopital's rule. Natural log of y equals the limit as x approaches 0 on the plus side of, here we go. What, good practice, what is the derivative of the natural log of 1 minus 7x? Outstanding. Derivative of natural log of a function, got to know these rules, chain rule version, is 1 over the function times derivative of the function. So it's going to be 1 over 1 minus 7x times the derivative of the inside. What's the derivative of 1 minus 7x? Negative 7. Divided by the derivative of the denominator. What's the derivative of x with respect to x? 1. So now, clean it up. You end up getting the natural log of y equals the limit as x approaches 0 on the plus side of negative 7 divided by 1 minus 7x divided by 1. Who cares? Now, plug in 0. This will be negative 7 over 1 minus 7 times 0 on the plus side. 7 times 0 is 0. 1 minus 0 is 1, so it's negative 7 over 1, which makes it negative 7. Is that my answer? Not quite. It's the natural log of y, the natural log of the answer. So therefore, the natural log of y equals negative 7. So what gets rid of the natural log again? E to both sides. So I end up getting y, which was the original problem, the limit as x approaches 0 on the plus side of 1 minus 7x raised to the 1 over x. And what's the answer? E to the negative 7. So, for the majority of these problems that are 0 to the 0, 1 to the infinity, infinity to the 0 power stuff, you're going to end up getting e to somebody because you got to do the log of both sides and you got to get rid of the log by doing e. So the traditional answer for this type of mess is always that e to somebody.
If you did like log base 10, would it be 10 to the negative 7 then? Like, could you switch it up?
Yeah, but then you got to do chain rule, and then you don't forget you got an adjusting factor times the natural log of 10, and then the natural log of 10s end up canceling. So you're back to where you started from with these derivatives. So why do any kind of other base? The natural log is always the best base. So always do natural log of both sides because it's easier to take derivative of and don't have to worry about adjusting factors. Does that make sense? Don't lose you guys anywhere. So this should help you out with the rest of those problems on the homework set, as well as getting you prepared for your test. So let's move on to the next section. No time like the present. Chapter 4.1. All right. Chapter 4 is another one of those application sections. I'm trying to show you guys the importance of this Calculus 1 derivative stuff. First things first, definition. We're going to be looking for absolute maxes and absolute min values and stuff. A function f of x has an absolute maximum at x equals c if f of c is greater than or equal to f of x for every point x in the domain. Similarly, f of x is equal to the absolute minimum at x equals c if f of c is less than or equal to f of x for every point x in the domain. What do you think of when you think of absolute maximums and absolute minimums of a particular function? Maximum, you should think high points. Minimum, you should think low points. If you have an absolute maximum, you've got one point that is higher than all the other points. Does that make sense? This is a maximum. An absolute minimum point will be the smaller or the lowest point. The lowest point for the entire function is plotted at this x equals c. And that's all this is saying. We're talking about absolute maxes and absolute mins. And you ask yourself, why is this kind of important? Well, lots of reasons. But what we're going to be going after is this, trying to identify these maximums and these minimums. Case in point, I had a question for you guys. You guys are now in college. It's time for you guys to get a clue. How do you guys make money? We're Americans. Our job in life is to make money so we can have more stuff. So, how do we make money? We work. Yeah, okay. Well, I work, and then I pay bills, and then I have very little left at the end of the day. Okay? The reality of working. I work a lot, and I have 2 kids. And we typically spend more than I actually kind of have coming into the household, which means I got to have a plan. What's my plan to have the family make money? I've got 2 kids, and trust me, they're going to college. They don't have a choice. So, and being that they're my kids, scholarships may not be in their future. I never got scholarships. I was on Mama Papa scholarship. My parents were so proud. So, that being the case, how am I going to afford their future, college, or my retirement, okay, or basically I just had to put some new tires on my car. I had to have money. Yeah, I used a credit card, granted, but I had to pay it off at the end of the month because credit cards will mess you up if you don't worry about that. So, how do you make money? How do I invest for the future? Things like that. Well, right now I can put money in the bank, and I do. I put a little money in the bank, and that helps me with the tires and stuff like that on the car. But how much money do you earn in interest? How do you earn money in the bank? What's the interest rates these days at the bank? Low. Almost nothing, 0.5%, 1% if you're real good and you got some money at the State Employees Credit Union. They're the best game in town right now, and it's 1%. As I mentioned to you guys before, better rates in World War II. It's kind of sad. So, how do I make money? What am I going to do? How does everybody else make money in America? You invest. Invest where? Stocks and bonds and things like that. How do you make money in stocks and bonds? Now, granted, I have a bunch of money in mutual funds. So I kind of ride the wave of the stock market. When the stock market is up, I make money. When the stock market's down, I cry. So this is how you make money. I don't go to Vegas and gamble, but in a way, I am kind of gambling in the stock market. I'm hoping for that upward trend, and I surely don't want a downward trend. But if I'm really going to get into this market concept, how do you make money in the market? Well, what's the rule? You buy and sell. You buy and sell. And how do you buy and sell? You buy low and sell high, and the difference between the two is called profit, and then you got to pay your capital gains tax. But still, you buy low and sell high. How do you identify high and low? Max and mins. There's a mathematical procedure that I need to follow the trends. If I can figure out where approximate high is going to be at, that's the point where I want to start selling these particular stocks and then take that money and then maybe buy something else. And I want to buy it when it's low. I want to sell it when it's high. And then the difference between the two is just pure money in my pocket. That's really how you make money in the stock market type thing here. Now, granted, most of us, we put money in the stock market and then we hoping that our financial consultant, our accountant, and the guy you invest with actually knows what he's doing, and he's going to try to help you out with these highs and lows. But typically, we let the market run with mutual funds and things like that. But when you take your own personal interest in this and you try to invest money yourself, you're looking for these highs and lows and looking for trends. That's how you're going to make money. So there's a lot of mathematics behind this, and it's important. Okay? Not only that, I want to build something or other. What do I want to build? I don't know. I'm going to build a box. Really cool box for my kids to put their toys in. All right. What do we want to have? I want the biggest box possible, right? Because they got lots of toys. But I've only got a certain amount of material. So I would like to maximize the volume, but at the same time, I would also like to minimize the cost in making this here box. You see what I'm trying to get at? I'm trying to motivate you on why this stuff is so important. Maximizing and minimizing. It's huge all the way across the board and all the way up through your math and college career and then after college. It's that important. So, how do we identify these things? Here we go. We have absolute max and mins. These are extreme values, the biggest and the smallest point for the entire function. We also have something called relative or local max and mins. A function f of x has a local maximum at x equals c if f of c is greater than or equal to f of x at every point that is quote-unquote near C. So let me show you what I'm talking about here. If you got some kind of function that does this. There's my function. I just drew something rather. There are two maximum points on this thing. There is this point right here, and there is this point right here. You with me? This point is called the absolute maximum. Why? It is the biggest point on the entire graph. This guy right here, he is also a maximum, but we will call him a local or relative maximum. He's the biggest point in a little neighborhood around this point, but if you go down the road far enough, you may find bigger points. Does that make sense? That's what we mean by local. He is in a local neighborhood around this guy. He's the biggest point around. But if you drive down the road far enough, you may end up getting bigger points, which is what happens. So identifying the difference between local or relative versus absolute. And of course, if you have local maximums, you also have local minimums. A local minimum at x equals c means f of c is less or equal to f of x. It's the smallest point near c. But if you drive down the road far enough, you may get some smaller points. Does that make sense? All right. So this is what we call local. This is called absolute. Okay? An extreme value theorem. The extreme value theorem. If f of x is continuous on a closed interval between a and b, then f of x attains both a maximum and a minimum value, and these will be absolute maximums, and I can put ABS on this thing. Absolute maximum and absolute minimum value on that closed interval. As long as you got a closed interval, you are guaranteed there's going to be an absolute max and absolute min. Now, these absolute max and mins may be inside your function or they may be on the endpoints, but there will be a guaranteed, if you got a closed interval, there's going to be a biggest point on this whole thing and there's going to be a smallest point on this whole thing. There'll be an absolute max and absolute min. That's called the extreme value theorem. Fermat, not Fermat's last theorem. Fermat had lots of theorems. Here's one of Fermat's theorems here. If f of x has a local maximum minimum at c, and f prime of c exists, then f prime of c is equal to 0. What Fermat focused on was this. If you look at these maximums and minimums, and I'll give you some interesting function that looks like this. There's a maximum and a minimum on this particular graph. There's one right here, and there's one right here. They're local. They're not absolute, because I'll go down the road far enough, I'll continue to get bigger and bigger and bigger, or smaller and smaller and smaller. But now look at it from a calculus perspective. What's so darn special about these 2 points? When I take its derivative, what kind of derivative am I going to get? Well, both the maximums and minimums have horizontal tangent lines. And horizontal lines have slope equal to what? 0. So, and remember the derivative is the slope of the tangent line, so 2 and 2 makes 4, which means the derivative at these points is going to be 0. That's what Fermat stated. Maximum minimums, if the derivative exists, the derivative is going to have to be 0 at these maximums and minimums. Okay? When does a derivative not exist? Well, we have some special cases like the cusp, that sharp turn, and things like that. You could have a maximum minimum there too. We'll talk about that later. But for the most part, if the derivative exists, the derivatives have to be 0 at these max and mins. Critical number, fancy word. A critical number of a function f of x is a number c in the domain such that f prime of c is equal to 0 or f prime of c doesn't exist. I told you there were spots that the derivative doesn't exist at. If f of x is a local maximum minimum at c, then c is a critical number of f of x. Critical numbers are our fancy words for where these places where the derivative is equal to 0 and derivative doesn't exist at. Okay? So we're going to be looking for critical numbers because these critical numbers end up being the max bins. Does that make sense? And then we got one more clause, the closed interval method, which is a procedure that connected to the extreme value theorem that stated this. To find an absolute maximum minimum that is continuous f of x over a closed interval, here are the steps involved. You got to find the critical numbers. You find critical numbers by taking the derivative, setting it equal to 0 and solving. And you also check your endpoints, and then you plot the points and you compare, because here's the real deal. These critical points and endpoints, when you plot points, the guy with the largest y coordinate is the maximum. The guy with the smallest y coordinate is the minimum. This is how you judge who is maximum and who is minimum. We made a theorem out of this thing. So we got lots of problems to encounter. Please watch the awesome pre-section video on this stuff, and I'll be working on this stuff next time with you guys. Study hard, and I'll see you guys on Thursday. Don't forget, homework sets due before then. Thank you.